presentation will move forward with everyone on mute. As you have questions, please email them through the GoToMeeting system on the right. If you enter your question, if you have questions and you enter them into the text box, we'll get the questions and Lance will sort through them while I'm going through the web presentation. Again, thanks for being here, and we'll get going. I'm Andy Adams with W&M Environmental Group. I'm a senior consultant, and I'm the regional manager for the Gulf Coast region. I'm a little bit of a rarity in this business. I've worked with W&M for 10 years, and outside of research opportunities before this, W&M has been my only employer. I have a BS in Environmental Studies from the University of Kansas and a master's from the School of Public Health from the University of Minnesota. Most of my education, research, thesis, and professional life have revolved around fate, transport, and degradation of environmental pollutants and the interaction they have with exposure, risk, and effects on human and ecological health. As you might guess, with those interests, I spend a large amount of time working on what I like to call an integrated site closure, which really could be sort of code word for big messes. They're complex, mixed, gooey messes, multiple chemicals, multiple sources, multiple classes of chemicals in many different media phases. We usually see these types of issues at industrial, petrochemical, chemical, and manufacturing facilities. These types of problems often use the rules that are in place to the maximum extent. And what I mean by that is we get into using risk-based corrective action adjustments of the environmental standards, removal of non-aqueous phase liquids. And so non-aqueous phase liquids is really fancy for liquids that separate from water. We often call these NAPL, N-A-P-L. And often chemical or biological remediation or bioremediation. I like these cleanups because there's a lot of moving pieces. But for many of you on the line right now, the single biggest reason I think this talk will be helpful is to give you insight into when to do what. When should you recover NAPL? When shouldn't you? When should you monitor for a long time? When should you do injections? What should you inject? As a side, you know, my grandmother used to tell me if you can't explain it to your bartender, don't bother because no one else will care. So as we move through this, I hope to help you understand some pretty advanced concepts with some pretty down-home common sense. To remediate or not, that's the question, right? Well, maybe not exactly. If you don't take away anything else from this talk, I want you to remember three main points. The first is pump and treat is never the only answer. It may be part of the solution, but never the whole solution. And, you know, what do I mean by that? There are places where pump and treat makes sense. But if an environmental consultant ever comes to you and says that pump and treat and monitoring is the only solution, you should run away as quick as possible and make sure you don't leave your wallet behind. Pump and treat can be used, but after you exhaust every other possibility under the sun. We'll get into why that is later in the talk, but in short, that's Yogi Bear on the right saying pump and treat is never over until it's over, which is often never. The second thing that I want you to take away, do everything that you can do to use risk-based corrective action. Risk-based corrective action is a pretty fancy way to say, let's fit the concentration of methyl ethyl death. I'm going to use that term through this presentation, but insert whatever chemical you have at your site, benzene, toluene, NAPL, PCE, TCE, whatever the chemical. The point is that risk-based corrective action fits a site-specific condition to the level of methyl ethyl death that can stay in the soil or groundwater. That makes sense in a site-specific condition and won't harm, that won't harm people or the environment. The amount of methyl ethyl death that will cause harm depends on the exposure scenario. In most cases, you can influence, control, or alter those scenarios. Hey, Lance, I'm getting a little background on the line. Is there maybe a phone that needs to be muted?
You know what? I will mute myself.
Thanks. Sorry about that, everybody. You know, back to altering exposure scenarios. For instance, there are states that have ordinances that prohibit the drinking of groundwater. Ingestion of the groundwater is usually the most direct route of exposure and the most toxicologically relevant, meaning it is the lowest standard threshold usually. So by removing the drinking water pathway, we remove the lowest pathway that develops a standard, which, you know, in plain spoken language, it means the amount of methyl ethyl death that can stay at the site increases. That's good for somebody that's trying to clean it up. So we can also change the land use scenarios in many cases and make things only available for commercial industrial development. When we don't have to worry about 40-pound little Joey eating dirt out in the front yard, the amount of methyl ethyl death that we can leave at the site can go up. Most state standards for methyl ethyl death are set to the most conservative scenario. And what that means is shallow groundwater in a low pH environment in sand with a water well at the point of exposure, meaning the place where the chemical was spilled. These scenarios don't often happen, and you can usually adjust the scenario to match the scenario you really have. This usually increases the standard and the amount of methyl ethyl death that can be left on site. Exposure scenarios are something else that we can look into and can help in certain situations. These are much less common than some of the other adjustments. The last thing, the third thing, make sure when you have to remediate, you are doing the correct remediation mechanism for the concentrations identified. There is a clear progression for matching up the concentrations of methyl ethyl death with how to remove it. Remediation is also where you have the most cost associated with action. If you can remove something by grabbing NAPL or grabbing methyl ethyl death with a bucket or a skimmer, don't try to apply a chemical to it to treat it. Remove it with a bucket by grabbing it. It costs a lot less in that scenario. This will be a big part of the talk going forward, and we'll talk some about the basic rules of thumb for each type of remediation. Often at different points, all of them can be effective. And so looking at this, I thought it might be the best way to go about it to get some of the concepts across. I thought I'd tell you about one of the most complex sites I've ever seen, and you walk you through how we might approach it. So once upon a time, there was a marine terminal. The terminal had one primary line of business. They wanted to repair boats, ships, and barges. They started in 1952, and they would sandblast, repair, burr metal, and repaint barges and boats. As they did repairs, materials that were held in the boats, ships, and barges were also removed. Over time, they deposited the spent sandblast, scraped paint, metal repair burrs, dross, and all the contents from the holds and barges into an earthen impoundment. So the contents of the impoundment included solid waste that had chemicals of concern on them, crude oils, refined products, building block chemicals, chlorinated solvents, all from the holds of the barges and boat hulls. At the end of the day, just about all the normal suspects in most environmental investigations. Some of the chemicals of concern that we identified included total petroleum hydrocarbons, or TPH, volatile organic compounds, or VOCs, and semi-volatile organic compounds, or SVOCs, and also many metals. As the RCRA law came into being, they decided that it was a prudent move to remove the contents of the surface impoundment, and then they filled the impoundment in. And then over time, up from the ground came a bubbling crude, literally. So they installed sumps to recover the non-aqueous phase liquids, or NAPL. They recovered NAPL. They also started to do groundwater assessments, and they found, not surprisingly, more NAPL. TPH, VOCs, SVOCs, and metals, all at elevated concentrations. Some very elevated, to tell you the truth. In the early 1980s, a recovery well network was started, and most people would know this as pump and treat. And I will tell you at this point, this type of remediation made sense. They wanted to maintain hydrologic control, which is to say not have it moving out into the surface water. They also had NAPL in places that was fairly thick. You know, think feet of NAPL floating on groundwater. So in this case, pump and treat for some time period was likely correct. But I would always encourage someone to have a plan for after pump and treat. And, you know, ultimately, here's really why that is. This is what the plume of NAPL looked like in 1997. The purple blob is the area of NAPL identified. This is what the NAPL plume looked like in 2000. The white dashed line is the year 1997 NAPL plume size. The purple blob is the year 2000 NAPL plume size. This is what the NAPL plume looked like in 2004. The white dashed lines are the years 1997 and year 2000 NAPL plume size, and the purple blob is the 2004 NAPL plume size. And then finally, in 2010, there is no more NAPL. The white dashed lines are 97, 2000, and 2004 past NAPL plume sizes. And now I'll admit, this is an extreme example. Most places do not have enough NAPL for removal to take more than 13 years. But it illustrates an absolutely important point. Pump and treat and physical removal can remove NAPL. But at 2010, when this picture is taken, the site is not closed. Much less it's nowhere close to being closed. The NAPL is gone. But if you remember all those classes of chemicals that were identified, many of those chemicals are orders of magnitude above the state default standards. So this means that things like tetrachloroethylene, or PCE, trichloroethylene, or TCE, vinyl chloride, arsenic, and lead are between 100 times, are between about 10 times for lead and arsenic, and 1,000 to 10,000 times for PCE, TCE, and vinyl chloride above the default standard for cleanup. So, you know, some fairly low standards and some fairly high concentrations. Removing the NAPL was an absolute necessity and was really required before you can treat the groundwater for cleanup. But I think if we went back and reviewed this site, they should have started a little bit earlier on planning and putting into place the cleanup strategy before the NAPL was removed. And here's why. So what we have here is an illustrated view, and you'll see this graph in hundreds of reports where they're recovering NAPL or performing pump and treat on dissolved concentrations. On the x-axis, we have the concentration of methyl ethyl death. I'm sorry, on the y-axis, we have the concentration of methyl ethyl death, whatever it is, NAPL, benzene, PCE, TCE. And on the x-axis, we have days after the pumping started. When you have feet of NAPL or huge concentrations of PCE and TCE, you're justified to remove that material directly. In fact, it makes a lot of sense. The easiest, most common method is by pump and treat. But there are also skimmers, exchange resins, dual phase extractions. These are all ideas based upon the principle that if you can grab a bunch of the material in a container, that's the easiest, cheapest method available to recover it. And when there is NAPL, or concentrations in the percent level range, and that's the important part. When there's NAPL or concentrations in the percent level range, I'd wholeheartedly agree. If you can see it, grab it and remove it. The reasons these types of treatment aren't the only solution for the long term, you often see the graph of recovery above. When concentrations are sky high and you have 4 feet of NAPL floating on top of your groundwater, concentrations or thickness of product quickly decrease. And the technology for that specific instance is the right technology. We'll get to a graph on when's the right technology for recovery in just a bit. But once you get to a certain point where the declination of the concentration starts to flatten out, we reach a point where your return on investment starts to decline, meaning the amount of money you're paying to physically remove the methyl ethyl death is going up, and the amount of methyl ethyl death removed is going down. You rarely ever get the groundwater to drinking water standard, which is represented by the red line that we've denoted on the chart. The line goes asymptotic, and that is based purely on physics. There's less material to grab, so you grab less material, which makes the declination proceed at a slower rate, and the rate continues to slow. It's a little bit of a self-defeating prophecy. Another way to think of this concept is half-life. It continues to decrease, but at a slowing rate. If you remember back to the main points I wanted you to take away, it was pump and treat was never the only solution. And this asymptotic phenomena that never gets to the groundwater standard is exactly why. Now, if you remember the next point, it's always use risk-based corrective action when it's available. So the next question becomes, can we adjust the groundwater ingestion standard with risk-based corrective action? There are really 2 ways to skin a cat when it comes to closure. One is bring the concentration of methyl ethyl death down to the drinking water standard, or we can adjust the standard above the present concentration of methyl ethyl death, which maybe is a little more like this. Here's the same graph. We've added an adjustment line to the graph. There are a few different scenarios that can be employed in this instance. One easy adjustment, if the property is not going to be used for residential development, you can institute a land use restriction. This allows us to use standards designed for commercial industrial land use. This adjustment, in some cases, increases the standard, which in turn allows increased concentrations to be left on site. A note on this, I know in many states the commercial industrial definition is much looser than you might think or suspect. Residential often does not include condominiums or high-rise residential, but on the other hand, it almost always does consider single-family housing as residential. So it a little bit depends on what you're doing with the development. Another type of adjustment that some states have implemented is the municipal setting designation, often referred to as MSD. What it does is it uses a local ordinance that puts in place a ban on accessing groundwater for a potable purpose. The reason this is significant, most state and federal laws are written with an impetus on protecting groundwater. And they also assume that someone will drill a drinking water well at the most impacted area of groundwater contamination. Whether that's even possible or remotely relevant to the situation, you always have to consider it. By putting an ordinance on the area of groundwater impact, we have provided the regulators with cover, and that we won't have folks installing water wells into the groundwater plume, and we give legal protection, making it an actual crime to do so. This allows us to not consider the drinking water standard for a site. And again, you'll remember that I identified earlier that the drinking water standard is often the most conservative of all the pathways that a chemical can affect humans. Once we remove the drinking water pathway, you adjust the new standard higher. You'll see on the chart, in some scenarios, after doing physical removal and adjusting the standard, you may be at a concentration of methyl ethyl death that is below the adjusted standard, in which case, in those scenarios, you might be eligible for closure. That's the point of always looking into risk-based corrective action. So the next normal question that comes up in this type of stuff, so one of the tricky things about NAPL specifically, sometimes it doesn't go away easily and continues to provide a sheen on the surface, or even a little more, like that middle picture that has chunks in it. By the way, the stuff on the lower right-hand corner is among the most sticky substances I've ever encountered. You might as well toss your clothes if it gets on them. So the question comes up, how do I know when it's asymptotic? And actually the question is usually, why isn't the concentration going down? And the answer to that is, well, you need enough monitoring data to give you a clue that you might be at that asymptotic level and not be getting the most bang for your buck in recovery. The other wild card is that different states treat NAPL differently. Some say it must be removed. Some say it doesn't. Almost all of them use the term, it must be recovered to the maximum extent practical. I'd like to tell you I could give you a definition of what that exactly means, but I can't. There are definitions out there. ITRC has a good definition of what they think it is. But you know, what really matters is what the regulator thinks the definition is. And what I usually tell people is that you have to give it the good old college try. They're likely to measure the definition against how much you tried to recover and how well you document how much you try to recover. So back to our storyline. The red line is a line around the marine terminal facility. It denotes the property boundaries. The blue box, again, is an area where the surface impoundment once was. The area that is outlined in yellow is the area that we applied 2 different risk-based corrective action adjustments to the standards. And you'll notice something else. Those risk-based action adjustments only needed to be performed on part of the property. I get the question, does it matter if you apply risk-based corrective action adjustments to the whole property or parts of properties? I tend to use the KISS principle, keep it simple, stupid, meaning if you don't need a restriction somewhere, don't put it everywhere. I'm sure there are plenty of folks who might disagree with me on that point, but going into the real estate world, they usually call these types of issues encumbrances, and at a base level, encumbered properties are usually worth a little bit less than unencumbered properties. And that, again, all depends on the encumbrance. And that, of course, depends on what the purchaser is buying it for. Many might not care in the least. But anyway, so what we did was we put two types of risk-based corrective action adjustments into this site. The reason being, going back to the three things I wanted you to remember, risk-based corrective action is cheaper than remediation. So the city assisted with us in putting an ordinance into effect, blocking access to the groundwater for potable purposes inside the yellow box. This increased the standard for groundwater concentrations and some soil concentrations. There were still impacts at the site above those adjusted standards, however. We then went further and put a commercial industrial land use restriction on the southern portion of the site in the yellow box. This increased the standard for some of the groundwater to air pathways at the site, which really what that did was further adjusted our critical state standard upwards even more. However, there were some fairly elevated concentrations at this site. Most sites, I'm going to tell you, those two adjustments would have moved us into being potentially eligible for closure. However, at this site, there were still impacts above the adjusted critical standard. So after we have adjusted our state standard up to as high as we can get it through the risk-based corrective action process, the next solution is to bring the concentrations of the impacts down. And as we've seen previously, that the impacts were being dealt with by pump and treat, and they had reached an asymptotic level above the standard. So in other words, we needed a different remediation technique. So let's look at high-level types of remediation scenarios. And so I really love this graphic, and it takes a little bit of explaining to really understand, so we'll spend a little bit of time on it. It actually comes from my friends at Regenesis. I want to make sure I give credit where it's due. And this is a fairly old concept, but when I see this chart, it really makes sense to me. On the y-axis, you have remediation effectiveness. I like to think of this as your return on investment type indicator. When the y variable is high, you're getting a lot of bang for your buck. And on the x-axis, we have decreasing contamination concentration. So this is the amount of methyl ethyl death that's in the system. So physical removal, this is again things like pump and treat, belt skimmers, oil water skimmers and separators, and dual phase extraction systems. It's massively effective when you have high concentrations of methyl ethyl death. And it decreases in effectiveness quickly as the concentrations decrease. This comes down to a concept of contact. If we are using a physical method to recover, there's got to be enough concentration to grab some of the methyl ethyl death. So think of it like this. If you have a bucket that you could dip into the groundwater, when it came out, if you could see some of the methyl ethyl death you were trying to recover, it's still an effective tool. Once you look in the bucket and you can't see any more material that you're trying to recover, then it's time to consider changing methods because your concentration is too low to use physical removal to be effective.
Hey, Andy?
So, yes, sir.
We have just a couple questions. Do you want me to wait for a minute, or do you want to answer them during the break?
Go ahead. You might as well get some of the questions out of the way.
What are the groundwater standards, and how do we maintain it, and what parameters do you test normally?
So the groundwater standards will always depend on what state you are. So in a state like Texas, where we do a lot of our work, those standards are PCLs. And there is actually a table produced by the TCEQ for those PCLs. And the way you maintain those is you look at you look at your monitoring data over time and make comparisons to those PCLs. Other states have a little bit different situations at times, but most states provide a table to go and look up things for default standards. Then when you get into risk-based corrective action, it takes some brain work, and that's usually where you bring in a specialty consultant to take a look at those for you and maybe calculate different things.
Okay, that was it.
Okay. So going back to this, when is physical removal useful? You know, it's really some pictures, I guess, is maybe the easiest way to take a look at it. So that's a belt skimmer in the lower right hand. It's pump and treat system in the upper right hand. MDPE, and then, you know, just some plain old NAPL recovery, however you get it out of the ground. Two things with this. Physical recovery is a grab type application. That bucket has to be able to grab a noticeable amount of chemical to make it effective. The second thing is, and this is a rule of thumb, you need more than around 100 parts per million depending on the chemical. Maybe that's 1,000 parts per million for things that are water soluble, and maybe that's 10 parts per million for things that aren't water soluble. Either way, if you can't see it being removed, or you can't run a sample and see 100 parts per million being removed in your discharge water, then it might be time to change recovery methods. And I'm going to switch over here to chemical remediation. And chemistry is absolutely a contact sport. You have to put the chemical into contact with the methyl ethyl death to be effective. So as we look at our graph, as physical removal becomes less effective at lower concentrations, chemical treatment becomes more effective. Chemical treatment can be done in a few differing ways. It can be done in situ. It can be done ex situ. The real point of either method of chemical treatment is that you put the treatment chemical into contact with the methyl ethyl death. The main part is that the two have to find each other. It doesn't matter if it's an oxidizing chemical, a reducing chemical, a reactive gate, etc. We have to get contact between the two of them. And so some examples of that include where we take some chemical and pump it into the ground, and this is in situ chemicals. You take a chemical and you pump it into the ground, and over on the right-hand side, lower right hand, you see some daylighting with a sheen on it, and the chemical basically gets injected, and it spreads out into contact with our methyl ethyl death in the aquifer. Now, daylighting is usually a bad thing because the chemical is not going into the ground. Some days it's unavoidable, but it makes for a good picture so you can see what's actually going on there. As the chemical enters into the ground, it then destroys or removes the methyl ethyl death from the system. Chemical injections can include a wide variety of chemicals: persulfate, permanganates, Fenton's reactions, other peroxides. And you know, you can also use ex situ type applications as well. This might include where you open up an excavation and sow chemicals back into the soil at the soil-water interface. Excuse me. Chemical remediation is effective where you can't grab a chemical anymore, meaning whatever's there, you can't just grab it in a bucket. There's still a good amount of it present, and a quick rule of thumb is it's less than 100 parts per million and more than 1 part per million. It can also be effective where you need to also treat the soil-water interface, and this is really saturated soil with methyl ethyl death, right where it hits the water. the groundwater. Pictorially, in the left-hand corner, we inject a chemical oxidizer into the subsurface through a well, and we are counting on there being enough chemical that it comes into contact with the red dots of methyl ethyl death. You know, those red dots running into the blue dots represents a chemical oxidizer. And in the whole point, there has to be contact between those two to make this work. The other thing with chemical remediation is rebound is likely, and rebound has tormented folks for years. Groundwater injections, I'm going to tell you, aren't hocus pocus, and there are reasons rebound happens to varying degrees. The hard part is that we don't always have enough data to identify what's going on. Rebound in general always happens to some degree. What we really hope is it's just not as effective at rebounding as some guy like Will Chamberlain or something along those lines. You don't want rebound to be so big because there might have been a better method to deal with it. So let's talk about what rebound is in chemical terms. It's a return to steady state. And right now you're all going, well, what's that? Steady state is just a term that really means everything has enough room and is comfortable. If we have 1,000 molecules of methyl ethyl death, for this particular methyl ethyl death, let's say 100 of them are in the groundwater and 900 of them are sorbed to the soil. For most chemicals that we'll ever deal with, the soil will have 100 to 1,000 times more mass of methyl ethyl death than the groundwater. There are a few exceptions, but those, like I said, are few and far between. But to walk you through a normal rebound scenario, the graph on the right side of the screen on the y-axis is the concentration of methyl ethyl death, and on the x-axis is days after treatment. When we start to inject at the top of the curve, we get good contact with the molecules in the groundwater and oxidize almost all of them. This changes the steady state of the system. Things get uncomfortable and they get out of place. There's basically free room. If you were a chemist, you'd call this free energy. In the groundwater, specifically, is where the free energy is because you've removed those molecules. So the soil and groundwater reposition the molecules for you. Some molecules come rushing out of the soil to fill those holes that we just created by oxidizing the groundwater molecules. That action is rebound. The concentrations in groundwater rebound back upwards. If we were monitoring groundwater concentrations fairly regularly, meaning every couple weeks, you'll often see the rebound overcompensate, and meaning more molecules come out of the soil than can fit into the groundwater comfortably. It basically overfills the groundwater with molecules of the methyl ethyl death, which is the little hump that I've labeled as reverse rebound. At some point a few months out, the wax and wane of the concentrations goes away, and we get back to a nice steady state concentration where both the groundwater and the soil concentrations are comfortable, and it's well below the original concentration in the groundwater. You know, quite honestly, some folks don't even know what rebound is because they just don't go out and monitor for the first couple of months after the injections. And then there are some folks, and I'm a little OCD, there are some folks that know it painstakingly well because they're out there 3 days after they did injections taking samples. There's a reason for rebound, and we want to make sure that we know where the steady state concentration is before we do too much more remediation. So as we go back to the graph, as chemical treatment becomes less effective at lower concentrations, biological treatment becomes more effective. chemical treatment as we go back becomes less effective because we can't get the chemical into contact with the limited amounts of methyl ethyl death left in the groundwater. Believe it or not, but 0.007 parts per million is a really small amount of material. But, you know, that's still often over the drinking water standard. So biological treatment or bioremediation is similar to running an end around in football. What we are actually doing is biological treatment. This is where we feed the, growing millions and millions of bacteria in the groundwater. And the bacteria are actually what treats the methyl ethyl death. They don't so much treat it, I guess, truthfully, as they use the methyl ethyl death as a food source. The reason biological treatment is good at low concentrations is because it isn't about contact so much. Biological treatment is a numbers game. If there are normally 10 to the 4th or 10 to the 5th bacteria in groundwater, we are looking to feed the bacteria and make the conditions comfortable enough for the bacteria to get up to 10 to the 7th or 10 to the 8th bacteria. Those increases of millions and those are increases of millions and millions of bacteria. The more bacteria and the more suitable the conditions, the more effective bioremediation can be. Some specific examples of nutrients or condition supplements include hydrogen release compound, molasses, methanol, lactoil, emulsified vegetable oil, cheese whey, oxygen release compounds, and I've truthfully only brushed the surface. There are a ton of different foods and condition enhancers for every chemical under the sun. While chlorinated solvents break down well in reducing anaerobic environments, petroleum hydrocarbons like oxygenated aerobic environments. So there are lots of different choices here. When is bioremediation successful? And the pictures are here more just commentary. Truthfully, it's boring to look at a real bacteria. So bioremediation is usually done by injecting nutrients or condition enhancers. Remember, we use bio when there isn't enough methyl ethyl death to gain contact. So instead, we use a natural community of bacteria to break it down. You normally need to be under about 1 part per million before contact becomes a problem. But many groundwater ingestion standards are 5 parts per billion, so an order of magnitude different. So there is still a fairly long ways to go to finish to that standard if you're just under 1 part per million. Bioremediation really involves the injection of nutrients or condition enhancers, which grows bacteria or makes conditions in the groundwater favorable for bacteria. And then the bacteria use the methyl ethyl death as a food source. As identified on the bottom of the pictorial illustration on the left, biology is absolutely a numbers game. You have to produce lots of bacteria to efficiently target the methyl ethyl death. So if we go back to our storyline, you'll remember that we sought an MSD and changed the land use to commercial industrial in the yellow area at the site. After we adjusted the standards up, we still had 1 methyl ethyl death that did not fall out below the standards that we adjusted to. Looking at the site, we quickly realized that the physical removal had gone asymptotic and that we needed to utilize a different approach. So we instituted chemical injections to oxidize our methyl ethyl death that was left. As you might expect, since this was a surface impoundment, there was quite a bit of impacted soils, which increases the amount of rebound that we see and the amount of chemical oxidation that's required. This site will never need bioremediation to gain closure. because we've adjusted the standards up using risk-based corrective action. Often the bioremediation element is a polishing step that needs to be performed in some areas that will require lower standards for closure. This site will never need biological treatment, but it's important to note biological treatment happens everywhere naturally. The rate at which it occurs changes and the conditions change, which affect its rate, but the bacteria are working naturally to attenuate the impacts, including at this site. So I'm going to switch gears and talk about bioremediation. At another site, to give you an example of bioremediation, but first we'll need a little bit of background. One of the most common bioremediation mechanisms in the environmental world is reductive dechlorination. It is often used on tetrachloroethylene or PCE and trichloroethylene or TCE, some of the most common environmental contaminants in the world. The mechanism of reduction is pretty simple on the surface. TCE has 4 chlorines. As we take a chlorine off at each step, we go from tetrachloroethylene to trichloroethylene to one of 3 types of dichloroethylene or DCE to vinyl chloride or VC. And you can blame some old chemist back in the day for not calling it monochloroethylene. I don't know why they diverged there. There is some amount of reductive dechlorination, and it's often referred to as natural attenuation that goes on at most sites. This is dependent upon the groundwater conditions and the amount of bacteria present. The way to manipulate the natural conditions is to force the aquifer to more favorable conditions for growing more bacteria. This is often done through an injectant. Again, as we talked about before, the nutrient that we inject isn't having a direct effect on the ethynes, the PCE and TCE. The nutrients that we inject are fueling bacteria, which in turn are multiplying, which in turn consumes chlorines from the ethynes. As they cleave off chlorines, we reduce the parent compound, which is the end goal. What we see in this graph is concentrations on the y-axis and date on the x-axis. Each arrow on the right-hand side of the graph is an injection of cheese whey. Why cheese whey? Well, because it was free and it has lots of nutrients in it. Some days you don't overthink things. What you can see is pretty typical for reductive dechlorination. TCE is the brown or red line, DCE is the blue line, and vinyl chloride is the yellow line. And again, so it goes TCE, DCE, vinyl chloride as it reduces down. After cheese whey injections, we see the TCE drop off the charts as it is degraded into DCE. And we see DCE initially rise, and over time we see DCE then drop off the chart. And then the VC, or vinyl chloride, rises. The VC is finally converted to ethene, which is a non-toxic gas that exits the system. This progression is typical for bacteria reduction. You'll notice there are quite a few injections of cheese whey at this site. The injectant is usually a large cost, and in this case the injectant was free, so we could do more injections. And a lot of that is based on where you are, what's available, how far it is, how much a truck is, all those good things. This is one more site I wanted to highlight. Here's another recent example of a Chemox injection combined with a bioremediation injection. We used a persulfate chemical oxidizer from Regenesis, and we combined that chemical injection with a bioremediation injection. The bioremediation injectant was cheese whey again, which we used again mostly because we could get it free from a cheese shop. But it also seems to work well. Note the TCE, the blue line with the triangle, after the injection, which is signified by the gray area on the chart on the right-hand side, drops to non-detect. While the vinyl chloride, the red line with the square, increases. This is the combined effort of the oxidized TCE from the chemical oxidation, combined with the effects of reductive dechlorination, progressing from the cheese whey and the reductive dechlorination process. This site is an example where we weren't able to adjust the standard up because of the location of the site, so we needed to have the biological polishing step to move the concentration down under the 1 part per million threshold. Again, as we wrap up here, if you don't take away anything else from this talk, I want you to remember the 3 main points. Pump and treat is never the only answer. It may be part of the solution, but it's never the whole solution. The second thing is do everything you can to use risk-based corrective action. The third is make sure when you remediate, you are doing the correct remediation mechanism for the concentrations that you have. Don't waste money throwing good after bad. And the last point that I'll bring up about sites, monitoring to monitor is not a solution. Make sure your monitoring has a point and will help you get to closure. And so as we get here, it was a pleasure speaking with you today. If you'd like a copy of this presentation, feel free to contact me. I've put my contact information up on the screen. I'd love to make it available to you if you'd like it. Additionally, if there are questions you might have, we'll have a short Q&A session now. Please drop us your question. And if you'd rather ask them offline, feel free to contact me at the contact information on the screen. Lance, have you had any more questions come in?
Yes, I do. I have 4 questions, actually. The first one is, when you add chemical injection to the groundwater, aren't you contaminating the water more, or does it just go away somehow?
Well, so I would tell you it depends on what you're injecting. There are, so permanganate, for instance, you're adding the manganate to the groundwater for a long time. On the other hand, we've accepted that we'd rather have that than we would TCE or PCE. And the reason being, TCE is a direct studied chemical at Camp Lejeune that causes a very high cancer risk to folks. For the most part, most of the injectants that we use go away fairly quick. They are not lingering, down there. In fact, most of them in the chemical side last only a couple weeks. On the biological side, they might last, at the most a couple years. Some far less than that. So it's a very noteworthy point. You don't want to do more harm than you already have, but for the most place, we've accepted that that these are good because they eliminate those cancer-causing chemicals, and they don't last a very long time.
Okay, the next question is, and you may have already answered this, I have PCE and TCE in the groundwater at my site. What do you suggest for treatment?
So I think the big thing for that question is it depends on the concentration. The first thing I would tell you, depending on what state you're in, let's try and adjust the standards for the state that you're in. And if we can do that, that is usually the most efficient, cheap way. If we can't adjust those above the concentrations that you have, you'd probably look at a chemical or a biological solution, and part of that can depend on your timeline horizon. Do you have, are you going to operate on this site for 20 years? Let's do a cheaper method and do some biological treatment. Do you need it cleaned up before you sell it in 2 years? Well, maybe we need to rethink that and do a chemical injectant. And again, that's all dependent upon the concentration.
Okay. Next question is, I have NAPL in the groundwater. I want to expedite closure. How should I handle it?
Well, so if you have NAPL on your groundwater and you want to expedite closure, you need to start recovering the NAPL. And so that's a physical removal type application usually. So you got to go and look at what your geology is, how it got there, how old it is it volatile, is it gasoline? You know, you do different techniques of physical removal, but the first step is physical removal. And then we'd really want to know the dissolved concentrations to make sure that we look ahead and look at the standards that you'd need to meet in the future so we could start moving towards that process now. I hope that answered that question.
Okay. The last question I have is, I have monitoring data that shows MNA is occurring, but I've been monitoring for 8 years. Do you have any suggestions how to speed it up, and will it ever get done?
So towards the last slide, I said monitoring to monitor is not a solution. So if you have MNA occurring, that's great. That means that you have a natural population of bacteria that are breaking down whatever the contaminant is that you have. So one way to expedite that is, let's help them. Let's take a look at what the groundwater is like. Let's give them, if it's a petroleum product, let's give them some more oxygen and some aerobic conditions in your aquifer. Or if it's a chlorinated solvent, let's give them an anaerobic atmosphere by adding some emulsified vegetable oil, or you know, take your pick, cheese whey. You can speed it up by increasing the amount of bacteria that are there. That's a cheap option, and you're already at 8 years, so I assume that time isn't expressingly important, meaning you have 2 or 3 years to increase those rates.
Okay, Andy, one more. Yeah, okay. I think that's good. We have one more question that just came in, and I'm might be out of my league here, but it says, can we get a certificate of participation or confirmation email so that the hour can be used for continuing professional development?
Yeah, we can absolutely get a certificate issued, and anybody that probably wants that, should I have him? You want to email you, Lance?
Yeah, that's fine. It's lfrench@wh-m.com.
Okay, well, I appreciate everybody joining today. If you have questions, please let me know, and would love to hear from you.
And Andy, I am going to send out the presentation this afternoon, and I'm also going to get the recording on YouTube so they can refer back to it at their convenience too.
Great.
All right.
Thanks
Thanks,
Lance.
guys.
Thanks,
All right.
everybody.